Hi, everyone. I appreciate the opportunity to speak at PLOTCON today. I know I'm the last person to speak, so I appreciate everyone staying this late. And I wanted to start by taking a brief survey of the audience and ask how many of you guys work with large data sets? Let's say records over 100 million records. Show of hands. What about 1 billion objects? Any folks there? Wow, that's pretty good. How about, the folks that work with large data sets, how many of you guys spend more than, let's say, 10, 15 seconds waiting for your analytics and visualizations to complete? That's pretty expected. So imagine if you had a technology that could serve as your data warehouse, run your analytics, and visualize your data in sub-second time. Wouldn't that be great? I'm Amit, CEO and co-founder of Kinetica, a GPU-accelerated in-memory database. And in the next 20 minutes, I'm going to share with you how we're solving the complex challenges of processing large data streams, running your analytics, and visualizing that data in sub-second time. All right, so I know firsthand these challenges as I spent the past decade working with the NSA and the US Army battling terrorism at a global scale. My last principal project was called the Brain Project, and we were moving from like a document-based search to entity-based search, where we were ingesting over 200 different data feeds coming from a variety of different sensors. This included data coming from drones flying in the air, mobile devices that are emitting their metadata every 1 second, and then also, let's say, like open social data feeds such as Twitter and Facebook. And one of the hardest data feeds to process in real time is cyber data, as it's constantly changing, never stopping, and coming in so fast. So it's, our Intel analysts had a problem, and they really didn't know what to search about. They were essentially trying to find a needle in the haystack. So, the project that I worked on, they had an unlimited budget, so we could pick any technology we wanted to. We had enterprise licenses for Oracle and SAP, had hundreds of nodes of Netezza. We had acres of Hadoop, if you can imagine that. And I remember, back in 2008, 2009, we started from a relational database and moved to Cassandra. And we liked Cassandra very much as you could ingest data very quickly, but the fact that it had eventual consistency, we migrated to HBase. And we used HBase for a good amount of time, but then we saw there were a number of different security holes within HBase. So eventually, my military leadership created a Cumulo. And I'm sure maybe some of you guys heard of a Cumulo. This was actually given to the open source community, and it became an Apache project. Another technology out of my military leadership was NiFi as well, or Niagara files. So we were one of the few technologies that was commercial, and this slide shows a highlight where we were in production in 2012 and migrated the organization from Oracle onto Kinetica. So some of the same challenges we see in the military, it was very evident in the commercial industry as well. And this is because, the explosion of data. So similarly, we have structured and unstructured data coming from Twitter and Facebook. Everyone has at least one cell phone, so, various different geospatial breadcrumbs coming out from this, and this phenomena of Internet of Things. So our first set of few customers were Fortune 10, Fortune 50 companies. So, it was very much like working for the military for these organizations as well, as they had pretty much every single technology under the sun. And many of the technologies, Oracle, SAP, we found they were I/O bound and or compute bound. And also organizations are going from COTS, and they were trying open source technologies, but a lot of times organizations are duct taping 5, 10 different technologies, and they can never get to production, as open source have different release cycles, and they're very loosely coupled together and very complex in using. So what we did was created a GPU-accelerated in-memory database, and we started from the ground up and aligned the data to the cores of the GPUs. So a typical GPU has around 4,000 to 5,000 cores per card, and you could put 2 to 4 of these cards in a single server. So essentially you have 10 to 20,000 physical cores operating for you, compared to the CPU-based technologies where you have just 10, 20 cores per socket. So we say we're giga-threading per node rather than multi-threading per node. And yeah, we started as a geospatial and temporal computational engine, and through the years, we became a full-fledged, highly available distributed database. And built into our database, we have NLP-based full-text search. So we can do regular types of full-text search, like wildcard characters, but also more sophisticated type of searching, such as n-grams, fuzzy logic search, and things of that nature, which I'll show you an example of. And we linearly scale out, so and this can be on-premise or in the cloud. So we have instances on EC2 for Amazon, Azure, but we have great partners to include IBM, HP, and others as well, where we are in production with major customers. And we have deep integration with the open source community as well. So we can read and write HDFS files for Hadoop. We can write RDD files to and from Spark. And yeah, with our military technologies, we have deep integration with Niagara files and Apache Accumula as well. And then built into our database, we have ODBC and JDBC connectors. So BI tools such as Tableau and other types can take advantage of this interface, and we're just slinging SQL back and forth. And then one thing that separates us from other operational databases is that we have a distributed visualization pipeline. So using the same GPUs that render video games, we use these to render pictures and videos that are created on the fly. So we can render billions of objects in sub-second time. And one of the largest bottlenecks in the software architecture stack is moving data from the database to the analytics engine to the visualization engine. So because you have to serialize millions and billions of objects, we can essentially short-circuit this, keep the data at rest, and do everything in a single technology. So we'd like to say, we're trying to have an Apple experience. So serve as your data warehouse, run your analytics, and visualize your data in a single product. So this is a case study of a large retailer. It's a Fortune 10 retailer, and the technology they were using was SAP HANA, very expensive solution, and this was running on a scale-up hardware costing over $10 million. As we linearly scale out on commodity hardware with GPUs, we were able to do complex queries that took HANA 30, 40 seconds to do in sub-second time. And so they gave us 10 queries that caused HANA to crash, especially once you get large streaming data sets coming in. So they had a 150 billion fact table, and then joining this with a 50 million dimensional table. And we could do this in sub-second time, run various different aggregations and groupings, and also visualize their data on dashboards. And another test was ingestion. So we actually had a 20-node Hadoop cluster that we ran a bulk ingest job on, and on a 10-node Kinetica cluster, we were ingesting at 4 billion objects a minute with primary key off, and 1.3 billion objects a minute with primary key on. And each row had 70 different attributes. So this, we can do pretty fast ingest, run analytics, and visualization simultaneously. So this is pretty different than other databases out there. And this is because we don't have to index and delta index, which causes many technologies to be batch-oriented and can't process in real time. So another one, this is one of the top 5 large telcos, and this was against Oracle Exadata. And similarly, Oracle Exadata wasn't as fast as our use cases with HANA, and these queries were taking several minutes to conduct. And again, this was against 2 billion rows, joining with a 50 million fact table. And we could do this in sub-second time as well. And this was just on 2 nodes compared to a rack of Oracle Exadata. So we can't wait till Oracle finishes, so we'll go to the next slide. Like I mentioned before, we have great partners hardware-wise, and we linearly scale out. So your typical node looks like a Spark node, and on average, we see our deployments with a half a terabyte of RAM to a terabyte of RAM, and we have big instances. USPS is one of our major customers since 2014, where we were 5 nines highly available, and they have 60 to 80 nodes where with terabytes of data processing real time, and we have over 20,000 users hitting us simultaneously every day. So pretty big customers that we have large deployments into. This shows some additional customers across multiple different verticals, and yeah, I mean these are the top 10 customers per vertical. Some I can't identify, but you can see that. So how do we fit inside a reference architecture? So we can serve as the hot layer on top of a Hadoop cluster, or be the authoritative data store, where many production deployments we are. And we can ingest data from a variety of different data sources, and we have ODBC and JDB support, so we can have BI applications such as Tableau, Qlik, and others use us as a high-performance database. One thing that we added last year was user-defined functions, or UDFs, and we see AI and BI becoming very prevalent in today's technologies. So this allows you to, let's say, register TensorFlow or Caffe or Torch as a library and run a particular analytic or network against a table within Kinetica with billions of rows. And then you can do subset queries as well and filter the table that gets produced from your algorithm and have better analysis on doing machine learning. So as I mentioned, we started as a geospatial and temporal computational engine, and so with that we can store complex geospatial types, so points, lines, polygons, multi-points, and multi-polygons. So we store the data as WKT, or well-known text, which is an OGC standard, and then we emit that data as a KML or a WMS, which is a universal for geospatial clients. So with that, I can get into the demonstrations. All right, let's see. So I'm just going to refresh everything. This is our admin, and let me just make sure everything is refreshed. So this database has, if I go into stats here, it's an 8-node cluster with a half a terabyte of RAM per node, and each node has 4 GPUs. So I would say it has 10,000 GPU cores, and where the CPU cores are 12 cores per socket. And if I go into data, we look like a relational database. So we have multiple different tables here. This particular master data schema has almost 21 billion records. And if I go into this, and let's say I go to Twitter, we look like a relational database, right? So if I go into table info, we're strongly typed per column. And if I go here, you can see the Avro schema to define the table. And then we can annotate specific columns and say we want to store this just in disk, or we want to GPU accelerate this, or we want this to be text searchable. So there's a lot of flexibility that we give. And then if you want to declare primary key, foreign key relationship, you can do that. Just going to refresh this. So this demo is online, and every time I zoom in or out, it's a new picture that's generated by our database, and it's a 200 kilobyte PNG image, and this is around 828 million flight positions. And nothing is cached or indexed, so I can change the color scheme on the fly. I can make the blur radius very fine or very coarse. And let's say I can start running some queries and say, show me all flights with an origin of LAX. So very quickly, I go down from 828 million positions, scrolling down to 23 million positions. I can do an arbitrary timeline filter, so we don't require any, indexing based on time, last day, last month. You can just drag and drop your timeline and, see the results. And then let's say I want to say, show me all flights above this random number, 32,322 feet. So you can see it takes a little bit of distance before flights get above this altitude. So additionally, we can actually see all the vector data, and we give you fine-grained handles to the renderings as well. So this is millions of points. The blue points right now are the transition points, and I can change the size on the fly. I can change the color to be, pink, and turn on the lines. So, this looks like a blob right now, but if I keep drilling in, you can see the actual, transition points of each flight. So, not only can we just do points, but more sophisticated types of geospatial types, such as points, lines, polygons, and we support symbology as well. Pacific Gas and Electric is a major customer for us, where we basically consolidated all the different lines of businesses, and they run off of a single instantiation of Kinetica. But yeah, basically we're sending a PNG image, and we interpolate where you click on and get a handle to the metadata right here. So we have a number of different data sources. Twitter right now, this is a live data stream. Let me click this. This is over 4 billion objects, and this is all hitting, this, so if I go into data schema here, it's a Twitter data table that I was on. But I can do, the sparkles that you see are tweets that we're ingesting right now, and I can do a geospatial search and say, show me all tweets within this region. And very quickly, I go from 4 billion objects to 815 million objects. We recalculate the histogram on the fly. I'm going to say, show me all tweets within this time span. And then I'm going to do pre-star, so a full text search with a wildcard character. And now I get all tweets in that region, in that time frame, that should have pre-star mentioned in it. So you can see there's a handle to 650. Yeah, I don't know what I get. But yeah, you can see that. We also have a visualization framework, and we partnered with Airbnb. This is the Caravelle visualization framework. And we made a number of different dashboards. So I can go into, let's say, network. And this is actually analyzing the net flow data of our Kinetica network, where we have offices in Arlington and San Francisco, so you can see the concentrations there. And if I click on a location, you can see what we're storing as the IP address, if we're transmitting any bytes, the source destination IPs, and the event that's classified. So if I draw a polygon around this region, it's pretty interesting. So you can see that a majority of the events, our firewall is actually blocking this as there's kind of some malicious activity going on. And you can see the source IP address and destination IP address. And if I go, change the timeline filter, you can see how everything adjusts accordingly. All right, another thing I can show you is, so like I mentioned before, user-defined functions. This is becoming big in the financial sector for us. As I mentioned with machine learning, so Google TensorFlow, Caffe, and Torch, this financial organization wrote their own risk management algorithm. And they gave a number of different, so I can go into the data table right here. Let's see, data. Stocks. So this is 1.4 million records, and you can see the various different attributes, prices, high, low. And so this is, they uploaded their snippet of Python code, and we're running it as a user-defined function. So against the 1.4 million objects, we're running their algorithm through our GPU distributed pipeline, and you can see the results. So now I can do a database filter and say, show me the telecom sector. And I very quickly go down to 12,000 records, and I can run that same algorithm. And you can see the results there. So I'm going to try to, so this is a VM I'm going to load up. But this it's a Windows. Tableau, there's some integration. Tableau isn't as great on Mac as it is on Windows. But this is using our ODBC JDBC connector. And I want to make sure. I'm going to close this and restart it because it may be stale. So we're basically Tableau certified. We'll have a major announcement in a few weeks, but all that's being passed is SQL statements, and this is leveraging our ODBC connector. And this is hitting a taxi cab data set, and it has 1.1 million records. And then, essentially I can pick any type of dimension and run filters through it, and you get results in sub-second time. So we're really the heavy-duty military-grade database that enables organizations to run various different analytics seamlessly. So with that, 5 minutes left, and good for questions now. Any questions out there?
I scare easily. My question is, how are you working with designers to promote best practices in data visualization to avoid having the ability to create bad charts?
Yeah, so we're providing RESTful endpoints so we can be leveraged more as a database. And we want to work more and more with designers, but we're really focused in on the data warehousing and analytics and how enabling designers to show millions to billions of points. But it's definitely where we want, one area we want to push on, and we're going to get better at that.
So you use GPUs, but I'm just curious, have you ever considered using FPGAs or ASICs or anything else like that other than CPUs or GPUs, just out of curiosity?
When we started our company, we wanted to follow in the footsteps of Netezza, and I believe you're from IBM, right? So, I mean, FPGAs, you guys bought Netezza at the end. It takes a lot of time to program towards the FPGA, and they're very expensive as well. So we wanted to take commodity hardware, add GPUs to that, so we can do massive ingest, run very large analytics and visualizations, and in sub-second time, that's cost effective for a organization as well. So we're seeing results of 100x faster than regular databases out there on 1/10 of the hardware. Yep.
Sorry. So with that integration with Tableau, is there a theoretical, is there an upper limit to the amount of data points that you could visualize on Tableau?
So we linearly scale out. We have customers that have 50 nodes, 100 nodes, and our largest data set size is the cluster-wide system RAM. So let's say you have a 10-node cluster, each node has a terabyte of RAM. We can easily compute 10 terabytes worth of data that Tableau can hit.
Questions?
Good. All right. Thank you, everyone.